This is General Chemistry, cover the topic of gas, part 5. We continue looking at ideal gas law and its applications. Today, we will try to apply PV equal to nRT to compare gases in two different situations. First, we have to convert it to PV over NT equal to R. Since R is a constant, the value of PV over NT has to be a constant too. And if we have two situations of gas to compare, we can get P1V1 over N1T1 to be equal to P2V2 over N2T2. The left part is the gas in situation 1, and the right part is the gas in situation 2. So let's take a look at this formula in a little more detail. From this formula, we can see that we have at least 4 variables P, V, N, and T to play with. So first, let's try fixing N. Let's make the amount of gas or N stay the same throughout. When there's no change in N, we can cross it out. And we will get P1V1 over T1 equal to P2V2 over T2. And we call that combined gas law. Let's take a look at a couple of examples to help understanding this. Here we have a container with lid which is locked in place. Inside the container we have particles of gas. Here I portray 5 units of gas. It can be 5 particles or 5 moles, but let's say it's 5 units of gas inside the container. If the gas is heated, the temperature will change, and most likely the pressure will change too. So here we change T and P. Nonetheless, the amount of gas or N remains 5 units, still the same as before. Let's take a look at the second case then. Here, we're starting with the same gas container. But this time, we will lift the lid up and lock it, which means we increase the volume of the gas container. Nonetheless, the amount of the gas or N remains 5 units, the same as before. We can also lower the lid down and lock it. In this case, we change the volume by decreasing it. Again, the amount of the gas or N remains 5 units, the same as before. So these are the cases where N is unchanged, and we may be able to use this combined gas law to solve certain problems accordingly, depending on what information they give us in the exam. Let's take a look at PV over NT a little more. In this case, we can try fix N and T, the amount of gas and the temperature. When N and T are fixed, we can cross them out, and we can get P1V1 equal to P2V2, and we call that Boyle's law. For Boyle's law, let's say we have a container with a lid that connected to a piston, so this lid can move up and down accordingly. And inside this container still contain particles of gas. And when these particles of gas collide with the container's wall, that will contribute to pressure. If we increase the volume of the container, we create longer distance for gas particles to travel and to collide with the wall. This means the number of collisions of gas particles with the wall will decrease, and the pressure of the gas will decrease too. So if we increase, P will decrease, and if we decrease, P will increase. So P and V are inversely proportional to each other. And that brings us to another interesting point. From Boyle's law, we know that P times V has to be a constant, and we know that P and V are inversely proportional to each other. So here, when P is large, V is small, and when P is small, V is large. But sometimes it doesn't stop there. We know that P and V, if P is large, V is small, and if P is small, V is large. Sometimes they want to take a look at 1 over V. So 1 over V and V, if V is small, 1 over V is large, and if V is large, 1 over V is small. Sometimes they ask us to plot or take a look at P and 1 over V. So now we see that if P is large, 1 over V is large too. And if P is small, 1 over V will be small too. So P and 1 over V are pretty much directly proportional to each other. And if we want to graph them, we should be able to get something like this. A linear plot between P and 1 over V. Let's take a look at another situation then. Here we will try to fix N and P. And if there's no change in N and P, we can cross them out. And we should be able to get V1 over T1 equal to V2 over T2. And we call that Charles' law. In Charles' law, let's say we have a lid connecting to a piston again. And if that sample of gas is heated, the volume must increase too for the pressure to remain constant. So this means if T increase, V, which is volume, will increase too. And if T decrease, volume will decrease too. This means volume V and temperature T are directly proportional to each other. And again, that brings us to another interesting point. From Charles' law, we know that V over T has to be a constant, and V and T are directly proportional to each other. So if we want to plot that, we should get a linear graph. But please be aware that the temperature has to be in Kelvin. But we can also plot temperature in Celsius too. We know that T in Celsius equal to T in Kelvin minus 273. So if we want to plot V and T in Celsius, we should get something like this. Still linear graph with the x-axis extrapolated back. Let us take a look at the next case. Here, let's try fix N and V. If N and V stay constant, we can cross them out again. So you will get P1 over T1 equal to P2 over T2. And we call it Gay-Lussac law. For Gay-Lussac law, let's say we have a container with a locked lid. If the gas is heated, the gas particles will move with greater kinetic energy, and they will hit the container wall more often and with greater forces. This means the pressure of the gas will increase too. So if we have T, temperature increase, P will increase too. And if we have T decrease, then pressure will decrease too. So we can see that the pressure P and the temperature T are directly proportional to each other. So let's take a look at another one then. This is a little bit of a special case. We no longer fix N anymore, but this time we will try to fix P and T, making pressure and temperature remain the same throughout. That means we can cross out P and we can cross out T, and we will get V1 over N1 to be equal to V2 over N2, and we call that Avogadro's law. For Avogadro's law, let's say we have a container that is externally connected to a gas cylinder, and the gas can be pumped in or out of the container. When the container is kept at a constant pressure and temperature, and we pump the gas particles out of the container, the number of the particles in the container will decrease, and the volume have to decrease too in order to keep the pressure constant. But if we increase the number of the particles in the container, the volume of the container will have to increase too. So that is Avogadro's law. V and N are directly proportional to each other. Let's summarize a little bit. From the ideal gas law, PV equal to nRT, we can get P1 V1 over N1 T1 equal to P2 V2 over N2 T2 when we try to compare gas in two different situations. And from that, we can get many more formula or laws. We can get combined gas law, Charles' law, Boyle's law, Gay-Lussac law, and Avogadro's law. Just from one PV equal to nRT. Again, you do not need to try to memorize all of them. From the ideal gas, the only formula that you should remember is PV equal to nRT. And next time we will try look at some practice questions, and we'll try to apply this knowledge to solve certain problems.